In this video, we are going to build a manually controlled 2 by 2 matrix multiplier inside Logisim Evolution. In the previous video, we built the core, the combination logic that handles the actual multiplication. Today, we are going to build the full circuit around it. The memory, the addressing, the registers, and the wiring that ties everything together. If you haven't watched the previous video, I recommend doing that first since we will be directly using the core we built there. Let's get started. Go to the memory library and select the RAM component. Place two of them on the canvas. We will call these RAM A and RAM B. These will store the elements of our two input matrices. Now, open the properties of each RAM and make the following changes. Address bit, keep this at 8. This gives us 256 addressable locations, which is more than enough for a 2 by 2 matrix. Data bits, change this to A616. The reason for this is that the matrix values you are working with exceed the range of an 8-bit unsigned integer. An 8-bit value can store a maximum of 255. Our matrix elements go beyond that, so we need 16 bits to represent them correctly. If your matrix values are all below 255, you can keep data bits at 8. There is no issue with that. This is important. In the properties of both RAM A and RAM B, find the volatile setting and set it to non-volatile. Here's why this matters. A volatile in RAM loses all stored data the moment you reset the simulation. Since we are going to manually load our matrix values into these RAMs, we do not want to re-enter them every single time we hit reset. Non-volatile means the values stay in the memory for the entire session until you close the file to set both RAM A and RAM B to non-volatile. Next, go back to the memory library and pick the counter component, place it on the canvas. This will be our address counter. The job of address counter is straightforward. Our matrix elements are stored at sequential addresses inside the RAM. Address 0, 1, 2, 3. The counter steps through these addresses one by one, telling the RAM which value to output at any given moment. Let me explain the pins on the counter, because we will need to understand them when we wire everything up. The R means reset. Sets the counter back to 0. We will not use this pin right now, but it becomes important in later bits. M1 for load when high. High means when the current passing through the wire is 1 bit. We won't be using the R, M1, M2 and M4, but we will use the M3 for the 2 by 2 matrix multiplication. One more thing, we are sharing a single address counter between both RAM A and RAM B. The reason is simple. Element at address 0 in RAM A should multiply with the element at 0 in RAM B. Element at address 1 with address 1 and so on. Using one counter guarantees they stay in sync and also reduces the number of wires we have to manage. Bring a clock component from the wiring library. The clock generates a repeating signal that alternates between 1 and 0. Every component in your circuit that has a triangle shaped clock pin needs to be connected to this clock. You can also manually trigger the clock at any time using Control T, which is why we call this manually controlled circuit. You decide when the clock ticks. Connect the clock output to the clock input pin of the address counter. The output of address counter to the address input of both RAM and RAM B. If you see any wire turning orange, that is Logisim telling you there is a bit width mismatch somewhere. Once the error is resolved, you will notice that the cell at address 00000. Did I say that right? 00000. In each RAM becomes a slightly darker shade of gray compared to the other cells. That is Logisim's way of showing you which address is currently being counted to. If you see that your counter is correctly connected. The registers. Now we are going to add registers. Place 4 registers for RAM A and 4 registers for RAM B, a total of 8 registers. Each register corresponds to one element in our 2 by 2 matrix. A 2 by 2 matrix has 4 elements, so 4 registers per matrix. Here's why we need registers instead of connecting the RAM outputs directly to the core. A RAM outputs one value at a time. Whichever address is currently selected, but our matrix multiplication core needs all 4 values simultaneously, as you saw in the previous video. To compute the result, registers solve this by letting us capture each value as the address counter steps through memory. Register stores its input value on a rising clock edge, meaning it latches the data when the clock transitions from 0 to 1 until the next rising edge. Whatever value it captured stays locked at its input, at its output. With all the 8 registers in place, bring in your 2 by 2 matrix multiplication core, but that we built in the previous video. You can rotate the core by adjusting its properties, which helps with keeping the wiring clean. Arrange the core so that the input pins are facing registers and output pins have open space on the other side. Connect the output of each register to its corresponding input on the core. Double check your connections here. The core has a specific input pin for each matrix element. Wiring the wrong register to the wrong input will give you an incorrect result without any error from Logisim, since it is purely a logic mismatch, not a wiring error. Take your time with this step. This is where we will stop for part 1. At this point, you should have RAM A and RAM B storing your matrix values, both set to non-volatile. A shared address counter stepping through the both RAMs in sync, a clock driving the counter, and all 8 registers. 8 registers capturing and holding matrix elements, the core connected and ready to compute. In part 2, we will add RAM-C to store the output wire in the controlled buffers and run the full multiplication.